Thank you. So my goal today is to try to explain to you what light is. So that's what we're going to do here.
A photon.
Well, we can think of it as a photon, or we can think of it as a wave. And it's kind of both. All right, so let's start out here by imagining an electron. Okay. And we know that electrons have a negative charge. We know that they attract things that have a positive charge. This is going to be 4B. I'm going to have this weird little section in the middle before I get to section 5 because, I don't know, I kind of had to throw this in. So this will be like 5 days of something else, and then we get into talking about chapter 5, which are mixtures and stuff like that. Yes. Well, tough. You had to hear my long answer. Okay, so electrons, they attract particles to them, and we know that if a proton is very far away, it's going to have a small force of attraction, so let's draw a small arrow. And if an electron is much closer, it's going to have a bigger force of attraction. Yes, you should draw this. Now, it doesn't matter where the proton is, it only matters its distance. So whether it's here or it's here, if it's the same distance, it's going to have the same force of attraction. In fact, I could draw protons anywhere that same distance from the electron. I could put it here, 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 and it would have that same force of attraction. So actually I could draw a circle around this electron, and anywhere along this circle, these protons would have the same force of attraction because they're the same distance from the electron. And I could draw a circle this distance away, right? And anywhere that distance from the electron, they would have the same force of attraction as this proton does. It's just the distance that matters. And so I could actually draw a whole bunch of circles around my electron. That's not a circle.
None of these circles are something.
So I could draw a bunch of circles, and anywhere along the circle, you're going to have the same force of attraction because you're the same distance from the electron. And if I drew all these circles, what would this be called, these circles? It would be called an electric field.
Looks like a dog's talking.
Electric field. It's actually an electromagnetic field because wherever you have electricity, you also have magnetism. Okay, so we have an electric field. Now this electric field is felt from here all the way to the ends of the universe. Obviously, if you get pretty far away, it's going to be very, very weak, but it is felt throughout the whole universe. So the field, the effect of the field, doesn't happen instantaneously in the universe, right? Like if that electron wasn't there a minute ago and I popped it into existence this second, you'd feel it very close by, but you wouldn't feel it far away for a while. If the effect of the field would start propagating outwards at the speed of light. So if you're over on the moon, it'd be a few seconds or whatever. If you're at the sun, it'd be a few minutes before you feel this electron that I just made pop into existence this second. And then, billions of years later, you feel it on the other side of the universe. So the field moves outwards over time. Okay? Now, what if I took my electron and I moved it upwards? Move my electron up to here. Okay. What's going to happen? It's going to shift. Yeah, the field is going to shift upwards. The field will move up to here, the electric field. Stay focused because I'm going somewhere with this. So my field moves upwards, right? But remember, the field doesn't change everywhere in the universe all at once. It slowly changes outwards. So I move my electron up, the field shifts upward. And then a minute later, out here, you feel the field shift upwards. And then a minute after that, you feel the field out here shift upwards. And then as slowly farther and farther away, you can see the field has moved up. Okay? Now imagine this. What if I took my electron, and I move it up, and then I move it back down? Well, then farther out here, you would see the field go up and then come down. And then farther out here, a minute later, you would see it go up and down. And then out here, you would see it go up and down. Okay, and you feel the shift farther and farther away. It would look like a wave pulse. The field would move one time and it would pass by you. But what if I took my electron and I started bouncing it up and down over and over and over? What you would see far away is this. You would feel the field bouncing up and down, up and down, up and down. And the way we would draw this is like this. It would look like a wave. And this is called an electromagnetic wave. It's just an electric field bouncing up and down over and over, and that effect passing by you over time. And that's what light is. Light is an electromagnetic wave. All right. Now, can I erase it? Do we have this written down?
Yeah.
All right, I'll start up here. So there's a couple things we care about when it comes to waves. One thing is how many of these little up and down pulses pass us per unit time. How frequently does that happen? And so the measurement of this is called frequency. The frequency is simply the number of cycles, or wave pulses in this case, per second. Really, it could be per minute or per hour or per year, but for waves, we almost always use per second. So any time would be fine. So let me stop that. Let me give you the other one. And this is usually represented in my classroom with a lowercase f. Sometimes people use other symbols, but I'm using lowercase f. And then we have wavelength is the other thing we need to know about a wave. And this is simply the length of the wave. No, don't write that. Let's do distance between two crests. So this is a crest, the top of the wave. So the distance between these two, that will be the length of the wave. And for wavelength, we represent it with this little symbol here, which is a lambda.
That's a what?
It looks like an upside down Y, called lambda. That's what we use for wavelength. And the last thing you got to understand about these two is that they're inversely related. In other words, the more wave pulses per second that pass by you, the closer together these waves are going to be, which means the wavelength is going to get smaller. So frequency and wavelength are inversely related. Inverse relationship just means they're like reciprocals. If you double the wavelength, that means the frequency will be half. Or if you increase the frequency by a factor of 2, then the wavelength will be half as long. So as one goes up, the other one goes down. It's exactly by the same factor. Okay, now there are an infinite range of frequencies and wavelengths, right? From 0 to, infinite waves per second or whatever. And so we've divided these up into sections so that we can deal with them easier. All right? And so I'll give you those different sections now. And so this spectrum of wavelengths is called the electromagnetic spectrum. That's what I'll give you now. And this is just a way to divide up the various wavelengths so that you can kind of deal with them easier. And you can get an idea just by knowing where one falls in the spectrum. So we're going to start with the left, well, obviously the left side. On the left here, this is going to be the longest waves. Longest waves. Left side, low frequency, long waves. Long waves. So obviously the end of this spectrum should be infinity, right? An infinitely long wave. And then this end would be 0 wavelength. And so, go up from left to right. So the right side will be shortest waves. Which also means the left side is highest frequency and the right side is lowest frequency. but I'm just going to use wavelength since the two are related like that. All right, so the first section of the electromagnetic spectrum is made up of radio waves. So these are the longest waves that we deal with. Your radio does pick up radio waves. Your TV used to pick up radio waves when you used to have those big antennas on the back. CB radios, which we don't really use anymore, those things use radio waves for their signals. After radio waves, am I going to give you length here? No, yes, I don't know, absolutely that. After radio waves, we have, let me make sure I don't screw this up here, microwaves, right? Waves. And yes, microwave ovens do use microwaves, and some of them use the next higher band. Your cell phones are kind of in between radio waves and microwaves. Some are on one, some are on the other. Most cell phones nowadays are in the microwave band. Cordless phones, Wi-Fi, this all uses microwaves. The next shorter wavelength or higher energy is infrared waves. Something to understand here, these waves are also called radiation. They radiate out from things, right? And so when you talk about these ones, people don't use the word radiation because everybody thinks the word radiation is scary. All bodies give off some form of radiation. Your body gives off some waves of some form. And at the temperature that your body is, you give off infrared waves. That's why night vision goggles pick up infrared waves, because that's what's coming from you. You're generating those waves. Okay, and like I said, some microwave ovens use infrared also. I think satellite TV is one of these two. I'm not sure which one it is. It's in there somewhere. All right, so after this band, there's this very, very small band in here. It goes from a wavelength of about, the longer side, let's say roughly 600 nanometers on the left side to 400 nanometers on the right side. So nanometers, 1 billionth of a meter. So about 600 to 400 billionths of a meter. Those are the range. And on this band here is called visible light. So the light that you can see has wavelengths between 600 and 400 nanometers. On the left side of this band, you have red light. 600 is red, orange. And on the right side, you have blue. So 400 is blue, violet, right around there. So if you ever look at a rainbow, what you're looking at is different wavelengths, right? Red has the longest wavelength, then orange, yellow, what's after yellow? Green, and so on, up to blue, which is the shortest wavelength, or the highest frequency. Okay, after that, what's the next section? Yeah, exactly, UV, ultraviolet. Okay, ultraviolet. Ultraviolet, you know, is what makes you tan. It also causes genetic mutations, which is why we have evolution, also why we have cancer. X-rays are after that. So as we go from left to right, these are higher energy waves, right? And because of that, gamma rays, they're also more dangerous. X-rays, you know what they're used for, right? We use them in medical imaging, chest X-ray, CAT scans use X-rays, things like that. These ones here, and you don't have to draw this line, but if you go from ultraviolet up through X-rays and gamma rays, these are all called ionizing radiation. So they have enough energy to break atoms off of DNA and therefore cause genetic mutations, which means they cause cancer, right? Nothing blue light or lower causes cancer. These are all completely safe, which includes cell phones, which are in the microwave range, completely safe. But ultraviolet, X-rays, and gamma rays do cause cancer.
If you get an X-ray, you're going to get cancer?
Well, they can cause cancer. If you had 1,000 X-rays, it's very likely you would get cancer. If you had
So
one
like
X-ray,
1,000, but like if you have like 10.
it's not likely. So, you know, and that's something people always ask, right? So if X-rays can cause cancer, why do we do X-rays? But it's obviously a lot safer than, let me cut you open and look inside. It's much better to take an X-ray. It's a lot less dangerous than, you know, slicing people open just to look. So, you know, but they can. These can.
What does an MRI use?
MRIs use magnets and radio waves, and the radio waves are actually generated from your body and given off to the MRI. So they're very safe in that way, although they are dangerous in that they use such big magnets that if you had like a piece of metal in there, you could get killed in an MRI.
Oh,
But yeah, because like the MRI has like, the magnets are as strong as junkyard magnets basically. So if you took like an oxygen tank or something and sat it in that room, when you turn the MRI in, it would get sucked in there and kill you.
Like if someone had like metal plate and then it's.
Yeah, if you have any metal in your body that's magnetic, you can't go in the MRI. Even if it's not magnetic, I think because it would get hot and it'll burn you.
that's crazy.
All right, I'm done.
Not if it's only like a ligament. I mean, I probably could get that MRI, but
That's
it's
just the
scary.
one.
Something like that. They might